So I was just like making this exercise to have some numbers in my head that allows you to plan much better what you are going to do. Together with all the stellar populations that we will be able to resolve in the halo, there are also globular clusters. Okay, and so we will get integrated life of all these globular clusters, and we can use this integrated light also to get information. And also there is a very interesting combination we can do, because for some of the clusters, they were observed already with HST. Okay, so you have seen here the resolved stellar population of the clusters. I believe there are also James Webb proposals going on to keep going with these globular clusters. So we can combine the spectral, the integrated light from the JPCAN spectra with the populations that we resolve. And that I think can be a very interesting exercise to help the photometry and the spectrophotometry with each other. Together with the globular clusters, there are also all the dwarf spheroidal galaxies. For the pilot survey, we got Andromeda 1. I will talk a little bit about the pilot survey. And this is just PANDAS. Okay, so PANDAS was able to resolve individual stars in these dwarf spheroidal galaxies. So with J-Atlas, we should be able to do it too. But instead of getting just a broadband color magnitude diagram, we will get a photospectra, which I think is going to be very encouraging. Also, there are exercises. There are people putting fiber fetch and getting spectra for individual stars, but they suffer for selection effects. Okay, as you can see here, they need to select a population. We won't have this problem because we will get in everything that is on the field of view. So selection effects won't be a limitation for us. Just the magnitude limit. And also, this is with the Subaru telescope. They put a narrow band here, strategically sensitive to surface gravity, and you can see how well they can clean what is M31 from what is contamination from the Milky Way. So I think we should be able to do it better because we have a larger number of narrow filters. Also, PANDAS, because of this, was not able to clean very well this area of all the foreground stars from the Milky Way. We should be able to do it. Okay, so maybe we will even find new substructure that was hidden in the PANDAS survey because of this Milky Way foreground contamination. Okay, so together with the survey we are conducting here, there is already other kind of surveys. The idea is to combine all the photometry that exists with the new photometry that we're going to generate, because the goal is going to be a legacy survey. The goal is to create a tool that is going to be extremely useful for the future generation of astronomers. So, for example, if we put a catalog together in N31 and N33 with all the information that the narrow ones will allow us, for example, if someone is interested in carbon-enhanced stars or metal-poor stars, the starting point can be this J-Atlas survey. They can just make a selection with the information they have already, okay, and then go to a telescope follow-up fiber fed. So the idea is to create a lasting tool for the community. This is Andres was making this figure, and also I took the figure and I add other surveys to give you an idea what is the coverage. SPHEREX is here. SPHEREX is going down to magnitude 20, 21. We expect to go down magnitude 23, but still you can see where like HST, PANDAS, Roman has submitted a proposal for a dedicated N31 survey. So the idea is that, okay, you see that we are the only ones covering this blue region. That is where I will show you later, where the information for metallicity and alphas is. Okay, so the idea is just to create a master catalog combining all the photometric information. Okay, so where is the information here? These figures are from my thesis. I never thought I would to use my thesis again, so I was like, well, because the ideal was very whatever. Anyway, okay, so you can see here that this is just those are models. Okay, and just like I fix the temperature and I fix the temperature surface gravity and I change the metallicity and I change the alphas, so you can see where the information to get metallicities and alphas is going. So we need this blue part. That worries me because they are going to be just cold red giants, but what the information is here is in the blue region and reddening also. This is a beautiful paper from Paula. She circulated around, and I was very happy to see that because everybody is using machine learning. I have nothing against machine learning. It's great, but I'm so happy to see some classical modeling going on, okay? Just only not to get the stellar parameters, also try to see if we can get calcium, carbon, magnesium, okay? So this is Paula found, okay, that all the information is in the blue, okay? So we do need, if we want to get metallicities and even try other chemical species, we need to get these blue filters, okay? So yeah, I was very happy to see this work from Paula. That was me. I think that was me like the first month I was here in TEFCA, because I think I arrived and the early data release was happening. So I just Jan Lee and Johan team to run the pain in this early data release. So they got a training set from Lamos and they just run. I think this is what Adrian is also doing for his thesis. So I was happy. No priors, no any whatever. Like let's try to see. You have this star. This is redder. This is bluer. No. Okay, just run the pipeline. And okay, so this is just very early. Okay, so it looks like there's some problems in surface gravity. But I was happy to see that the metallicity information is there, and there is also alpha over iron. As I commented, there is a lot of work to do, and I think Andres and Adrian, we can comment on that. Also, that was me playing a little bit. It's like, okay, how far we can go, okay? So I just got the Phoenix model. This is a red giant star that we have in common with Apogee, and I was very happy to see that. I just ran a chi-square, I'm CMC, and I was thinking, okay, well, it looks like the stellar parameters are going to be able to recover that, okay? And hopefully maybe we can go even further. So one of the things I want to do with Andres also with the values is start to remove points here and to see when I don't have any kind of information arriving anymore, because that's going to help me to see if we need the 56 filters or we need 14 filters to do what we want to do, okay? So the next step is going to try to keep going with this. There is a summer student coming, Francisco Jose, who is going to help me to put all these catalogs together. And also, we are hiring a postdoc. We are just making the selection. The idea is that the postdoc also is going to work on this problem, trying to get the stellar parameters from the spectrophotometry and try to see how far we can go, even trying to measure abundances. As I commented, the information is there. This is a comparison between high-resolution spectra and the metallicity coming from J+ using the 12 fans. So the information we know is there, and we want to create it for the M31 and 33 halos. Another topic that is very hot right now, you can see that we have this bimodality in the Milky Way, what we call it the high alpha and the low alpha, associated with the classic thin and thick disk. So there is a lot of effort now trying to see if the disk of M33 also shows this bimodality. I believe with our Atlas and with the narrow bands, we will be able to explore also this problem, and in a very extended region, not just in a very limited area like people using James Webb. We cannot commit with this Webb, but this is very, very expensive. So maybe we can able to do that much cheaper. As I commented, there is a Rome Andromeda. There is a proposal going on. Also, Rome Andromeda was what to observe in 2 different epochs. So hopefully we will get proper motions, and that will be great, because if you combine the proper motions with abundances, you start to do what we call a chemodynamical analysis in these galaxies. So I'm pretty much looking forward to see if this proposal is affected. Hopefully it will. Okay. DESI is also observing. This is the results coming from DESI. As I said, they have a fiber fed, so they have to make a selection of stars before they go observing. We won't suffer from this selection, but obviously they are getting radial velocities. Radial velocities, I have been talking to Tony, and I'm very excited because we're going to explore the possibility to get radial velocities from the narrow bands. Okay, we can talk later because this is a little bit in parallel, but I'm very excited about the idea of trying to see how far we can go to get radial velocities. If it works, that's big. That's big. Subaru PFS, I think they're about to start. They are going to also put the fiber fed, and they are going to get this. This is great. I mean, it's like we can complement each other because we can use this spectra as a training set for a much larger catalog that we are going to put together with the Atlas. Okay, so also we talk about M31, M33. It looks very interesting. We just put a paper out where we found like a population of clusters that are in retrograde motion, and probably means that have been accreted. Okay, and especially because Gaia proper motions is also telling us that M33 is in the first infold, because they were thinking that whatever we see this word and whatever we see in the halo of M33 is because M31 is perturbing this galaxy. So it looks like M33 is coming to the local group with his own history. We have colleagues doing M-body simulations in the local group. We will use whatever is available once we have all the data to try to understand what theory is telling us and what observations are showing us. Much more, okay? Detection of symbiotic stars, we will be able to find them, okay? We can create a planetary nebula catalog. Extremely metal poor stars, also a very hot topic in the Milky Way. We will be able to do it in M31. The pilot survey, okay? A few months ago, the pilot survey was observed, okay? So we have been, there were some problems with the guided ascent, so we need to put the exposure time a little bit down, otherwise we're just getting, like a completely a very interesting PFS so of the tracking. So we have been started to look at the data. This is a work with Maximo Dalora, that he has a PFS photometry pipeline that he's going to visit us, and the idea is to put this PFS photometric pipeline in part of the UPAD, so also run all the surveys that we are generating in Javalambre through a point spread function photometry, which for crowded out areas is very important. So this is a very preliminary result from as you can see, we are not going as deep as we wanted now. We didn't co-op the image here, but I just wanted to say that this is the very first color magnitude diagram that we have put out of this project. So work in progress. Planning, okay? As I said, for the big proposal coming in a few months, we have to think carefully about how we are going to start this survey, and also start to prepare a working group. So everyone who is interested, we will have to start to get organized, because I think this is going to be a big survey, and also funding, fundamental, right? I'm planning to work on a IRC, I think this summer, because they have changed they have changed a little bit the conditions for one of the programs they have. So now I can get in one of them. So anyway, I'm going to try to ask for funding. So it's going to be difficult, but I think it deserves and needed. And I believe this is going to be a fascinating legacy survey that we can create for the community, together with all the science that we will be able to do. And I think that's it. Thank you so much.
Questions for Borja?
Fantastic idea.
Now we need to do it.
Yeah. I have some concepts, no, regarding the. I mean, I have no problem with the, let's say, the chart measure. Okay. But the alpha and quite. Well, we have done already some tests with the GIMPAS intercept of galaxies, and didn't work in a way that the kind of thing you like to measure, because the order of the error.
Yeah.
So it's going to be really tough. But you said that you're going to focus on the grid.
It's where the information is.
All the information
is where the information is, yeah.
But that information is very complicated. Because there is where, particularly for all the stars, the models clearly fail. Because non-entity things, in the modeling, for example,
yeah.
Felix do not perform well. Maybe I would suggest you try Mars.
Definitely. Yeah. I mean, the idea is to bring different stellar libraries. Exactly. We are not going just to focus on one.
Exactly. I think it's critical, because Purus forget it.
Yeah.
But the point is that the information there is mixed between big lines, like for example, the Carson HK.
Yes.
Heavily.
Yeah.
Okay. So, and the information that we're getting from the alpha is in a way it's the slope, because when we increase the magnesium, you decrease iron, you are decreasing the mass. And this is exactly what you are probably doing with mission. This increasing flux. So I think this is something all that, I mean, I'm just pointing out some kind of, let's say, things to think about. Or to try to, it's not so obvious.
Yeah. Together with the limitations of coming from models, also reddening, because I mean we can control the reddening from the Milky Way in the line of sight, but I'm worried about the reddening in the entering one because I don't think we have level maps like we have for the Milky Way. So reddening can be also, especially the blue.
Yeah. One more quick question. If not, we thank Jorge again. Now we listen to Jairo Alzate, and he's going to talk about the legacy multi-filter survey of the galactic anti-center with JST.
Hello, everyone. I would like to start this talk with this presentation with a very nice picture of the Milky Way, as seen from Earth, but basically pictured by Gaia. And here we can observe all the substructures that we can observe in the disk. And as Alessandro commented previously, there are a lot of things to talk about it in the stellar disk. And it deserves to take a look on it with the Havalambre Observatory. So in a schematic, let's make a quick review on the Milky Way for everybody who maybe forgot it, but I'm sure not, but for completeness of the thought, I put it here. We have the Milky Way have different components, have a stellar disk that can be divided. I will argue later why into disks. We can say the thin disk, or sometimes some people call the external disk. Yes, and the thick disk, or some people call it the internal. It also has a bulge, and if you see the other picture, you can observe that the bulge has is spark-shaped, and it has many spiral arms, and also the Milky Way has a stellar halo, which is made not only of the stars, but many globular clusters. It is well known, thanks to spectroscopic surveys, that we can split or we can gather the Milky Way stellar disk populations into groups, a high alpha group and a low alpha group. We are observing here in the horizontal axis the iron, and in the vertical axis the magnesium abundances. And you can see that we have two overdensities here, and the low alpha overdensity is linked to the populations in the thin disk, and the high alpha populations are linked to the populations of the thick disk. And this is a very interesting and very informative data about the history of the Milky Way, because we have also here a correlation with age. So this is one of the most frequently observed plots in many research papers. And there are behind of this result, you can study or you can read different proposals for formation scenarios for this configuration in this chemical space. For example, the two-fold model, radial migration of the stars, a large major. This is highly linked to the last major in the Milky Way, which is the Gaia-Enceladus galaxy. And, for example, from simulations, we know that the feedback can also produce this kind of configurations. So we also know that the halo is not an homogeneous structure. It has many substructures. And for example, we have stellar streams for satellite galaxies that had or have been or are being merged with the Milky Way. And people is constantly looking for this kind of streams in the Milky Way. So particularly in our group, we are interested on the stellar resolved stellar populations that can be characterized in this group of things. For example, you can characterize them in overdensities in the sky, on overdensities in the proper motion space, or you can also detect them or distinguish them in the color magnitude diagram. And particularly in the chemical space, is one of the most useful plots to distinguish different stellar populations, because as you can see, as you saw in the previous slide and here, the populations are very well separate in this kind of plots. So some open questions about the history of the formation of the Milky Way, particularly on the stellar disk, particularly because, as you already know, we are interested in observe the galactic epicenter. So there are open questions in the formation scenarios about the stellar disk. For example, how important were the satellite impacts in shaping the outer disk? And this is a topic that I am very interested in. And how did the outer disk and the inner disk form? Or is the monoceros ring part of the disk or an accreted galaxy? Are there undiscovered stellar streams in the anticeptor halo? Halo. where does the galactic disk actually end? I mean, we have a border, or there is a connection with the stellar halo. So these are hot open questions that many astronomers are researching today. And regarding the first question, I would like to show you this video. Maybe you already know it, about the interaction with the Milky Way and the Sagittarius galaxy, and how Sagittarius has been influencing the star formation history of the Milky Way. This is in the vertical axis, you have the star formation rate, and you can observe how the pericentric passages of Sagittarius have been enhancing the star formation of the Milky Way. But not only the star formation. If you observe this plot, for example, in the y-axis, in the horizontal axis, you can observe the galactic radius, and in the vertical axis, you can observe the vertical dispersion velocities. How you can find a gap in this average point of stars in the Milky Way. This work were made with apogee stars, and you can observe this gap in the vertical velocity relationship with the radius, and the average age in this radius are located more about 60 years ago, that which is very near to this first strong interaction with the Milky Way. So the satellite galaxies has an impact on shaping the disk. And this is evidence or clues about them. Okay, and we can also observe how the outer disk can form, or the thick disk form. In this result from Shannon and Riggs in 2022, we can observe how they found. What can I say? That they found a very sharp chemical enrichment in the formation or the history formation of the thick disk, and you can observe this very clear formation and we found something similar on using J+ photometry and performing isochrone fitting on CNG diagrams, and we can observe also here how the monoceros ring and the anticenter stream can be characterized chemically. In this case, with iron as function of magnesium as function of iron, and we can also observe the ages. Without ages typical of the thin disk, so there is still a discussion about if these streams are fissures of the excited thin disk or satellite galaxies. Let me see the time. Okay, and in different studies, in this case, to study all these phenomena in the Milky Way history, in the Milky Way disk history, or the Milky Way formation history, are particular of interest and very useful stellar ages, metallicity, or chemical abundances, and our workhorse, of course, Gaia. And with it, we can create, for example, from neural network analysis of the J plus photometry. Here, Andres Del Pino has demonstrated that we can recover chemical abundances from the photometry of J plus. You can see also Juan et al. To see works on getting abundances with photometry. And we also in my work in Alzate and collaborators, we also found that we in synergy with Gaia we can perform isochrone fitting and recover star formation history on the J plus photometry. And we also show that we can make maps of chemical abundances and find metallicity gradients. This big hole you see here is the gap that J plus and J plus have lack of observation. So it will be very interesting to observe this region to complement or to extend this analysis. Also, let's go to the proposal and the concept of J-gaps. It's a legacy program with the JPCAM and the JPass filters. Aiming to produce an homogeneous optical multiform path on a large area towards the Milky Way anticenter. And they will provide this kind of products: low resolution spectra, stellar atmospheric parameters, metallicity sensitive information, and large-scale chemodynamical gaps, obviously in synergy with Gaia. And why the galactic anticenter? It is very logic to select the galactic anticenter because it's a region with low stellar extinction. In comparison with the galactic center on any object direction, we have less the lower stellar clouding region, and we are observing. We have observing the region where we can study a transition between the disk and the halo, and also because it's a zone that can be highly affected by strong gravitational interactions with satellite galaxies and host stellar extreme overdensities that have been studied today, like the Monoceros ring anticenter and the undiscovered other streams. The goal of J-gaps is not getting competition with this large surface. The goal of J-gaps is to complement this surface and provide information where this surface can, let's say, have a lack of information. And in this case, for example, if we compare with Gaia pseudospectra in the Gaia DR3, for Gaia DR4, we will have a complete cover in this fine region when Gaia has a high signal to noise ratio. And the idea is that to cover this fine region between 20 and 22 magnitudes in the Y band, for this analysis and reach a further giant stars in the stellar disk and complement Gaia, because Gaia will provide also metallicities on this star in the stellar disk. And for this plot is showing you, for example, the stellar phases that you can observe as function of distance. You cannot, each line correspond to a apparent magnitude, so you can observe in this color magnitude diagram until what is the maximum distance that you can observe this star intense. For example, for magnitude 22, you can only observe low mass stars in a very short distance, but for the brighter stars, you can go to further distance. And the idea is to reach these stars and give a photospectra in this longer distance where Gaia could have problems to offer chemical information. And obviously we have the parallaxes in the case for Gaia DR4. We can build very nice stellar color magnitude diagrams, and therefore we can also recover star formation histories for this region of the Milky Way disk. And finally, this is a footprint for of the potential in case we have sometimes with the telescope and GPCam. This is just an illustrative example of what is the footprint that we will point to cover this and the center region. And maybe this is too large because I was playing with the GPCam tools, and I observed, for example, that for the half of this area, we will need more than 1,000 points. And if we choose time exposures of 60 seconds, we need to cover the half of this area, we will need, for just one trail, we will need about 60 hours of time, of telescope time. And so that is one of the things that I would like to know in this meeting. We also perform some model toys. We have galaxy model, for example, the Besançon galaxy model, and we can get the stellar content in a given direction for a given solid angle, the stellar content in that cone. And we can build images like this one, and we can add noise and check what is the effect of the crowding. So we can observe here, for example, what is the effect of the noise, and if we reject the blended sources, we can observe how the completeness of the sample is decreasing. So we are performing this to check what is the minimum latitude that we can observe in the galactic plane. In that case, I am happy that you have already pointed the telescope in crowded region, so that will be very informative for us. And yeah, for this meeting, I would like to get information about these 4 issues. For example, the compatibility with the reduction process in the crowded regions. How is we can what methodology we will use for get aperture photometry, or what is the maximum area that we can observe, and get a polished observation strategy for this survey. I am very happy to know that you got photometry in the galactic plane. You know? So me too. That is a good estimation for that. And yeah, I leave you with the concluding remarks. That's it.
Thanks, Jairo. Questions for Jairo?
Yeah.
Curiosity, I wonder if I missed it. Are you considering also using high band as a detection band, or are you going to use the narrow bands as detection band?
Yeah, good question. For the experiments, I have used the high band as the detection.
So that means
the reference magnitude.
So basically, you're observing 2 trays: the narrow band and the broadband high.
So next time I will try with a narrow one for just one tray, because that is another question. If we will use, well, that will depend on the conditions. If we will use one just tray or 1 or 2 trays.
But Alessandro is asking for the detection tray. Detection band, sorry.
Yeah.
Detection band, that's not the same. Yes, there is not that detection. Alexander?
One question regarding is going to be there global clusters, for example, stellar clusters in the field?
Yeah, it is.
Which way are you going to?
Yeah, there are several papers that have been detected globular cluster, open clusters along the galactic disk. For the moment, I don't know because I have never working with the detection of overdensities in the dim disk. But yes, that would be another science case to take into account. But yes, that is a common result in many papers. Yes, but for the moment, I don't have a methodology or an idea to exploit that data.
So,
Can I follow up on? Does anyone know what is the largest globular cluster? Like projected on Sky? Is it Omega Centauri? Projected on Sky.
I could go with Omega Sun as well,
right?
but yeah, I don't know in projection. Okay, it's really big.
Still,
It might
Omega.
not be a question. Anyway, let's see.
I'm just thinking about the size of a very big globular cluster compared with the field of view of JP Campbell.
No, it's smaller.
Very small. That's why I was asking.
Yeah. No, it's not even small.
So, not a question but a comment with mine. For those of you that you don't know how to what are you going to observe or the pointings or whatever, at 5:15 we have a session. Plan your project with JPCam. So please stay here and plan your project, and I will help you. I will do an example, but don't do my example. Do your example or what you want, and I can help you. For those online also. So those of you that have questions about planning your project, please plan your project at 5.
Or never again.
No, well, never again with me or near to you. Okay. Next speaker is Marcelo Borges Fernandez, which is online, I hope. And Marcelo is going to talk us about the massive anti-center cosmic survey in 14 filters. Hi, Marcelo.
Okay, good afternoon. Can you hear me?
Yes, we can.
Okay, so I will share my presentation. So can you see it, my presentation?
Yep.
Yes.
Okay, great. So good afternoon. And first of all, thank you, Javier, for the nice organization of this meeting. It's a very nice meeting. So concerning this proposal that I will present today, the authors of the proposal are myself and also Simone Daflon, Alessandro Ederoclit, and also the Resolve Stellar Population team. So I'll start this presentation talking about the massive stars, okay, which are the main focus of this presentation. So as you know, the massive stars are stars more massive than 8 solar masses. They are quite very luminous objects with 10 to the 4, 10 to the 7 solar luminosities, but they are not so hot, okay? There are some objects that are not so hot. We have objects with temperature higher than 3000 Kelvin. So we have spectral types from O to F or even later spectral types. But they are quite rare objects. Depending on the IMF, we have less than 5% of the stars in the galaxy that are massive stars. And these objects are located at the thin disk of the galaxy, mapping the spiral arms. And we have also some massive stars already identified in different galaxies, especially in the local group. And these stars are the progenitors of the core collapse supernovae, neutron stars, black holes, and also gravitational waves. So these objects, they are located in the upper part of the AGL diagram. So there you can find some known classes of massive stars, like the red supergiants, the LBVs, and also the Wolf-Rayet. However, despite their rarity, they have a fundamental role in the evolution of the host galaxy. So their ionizing radiation is responsible for the large amount of the global energy budget of the host galaxy. And their powerful radiation shapes the local interstellar medium forming the very famous 82 regions, okay? And the strong wind during the whole life of this object deposited large amount of momentum and energy into the local interstellar medium. And the combination of radiation and winds from multiple massive stars can trigger new star formation process, or even destroy their matinal molecular clouds. And they are good traces to derive the metallicity gradient in the galactic disk. In addition, the strong mass loss via winds and eruptions during the whole life of these stars is responsible by the interstellar enrichment by processed material. So these stars are the main sources of carbon, oxygen, and heavy elements to the interstellar medium. So these stars are responsible by the formation of the fundamental material for building planets and also for life. However, even considering the importance, there are still many open questions related to evolution and the internal process in these objects. So we don't know how is the complete evolutionary track of a massive stars, okay? So we don't know how they are formed. We don't know if they are formed by the collapse of the maternal cloud, or by the merge of several low-mass protostars. We don't even know how the massive star they evolved from the main sequence to the supernova explosion. We don't even know if all the massive stars explode as a supernova. And there is a poor comprehension of some process, like the convective overshooting, the chemical diffusion, and also the angular momentum transport. We don't even know how the mass loss and the winds are triggered, okay? Maybe due to the pulsations or the high rotation, due to binarity, or maybe the combination of everything. So there are many questions, and another question is about the origin and the whole of their magnetic fields. In addition, we don't know the link among the different evolutionary phases. We don't know the link between the blue supergiants, the red supergiants, the bibracteal supergiant, the LBVs, Wolf-Rayet, and the yellow hypergiants, for example. So definitely a detailed study of a large sample of massive stars is necessary to understand these very important objects. And we need to identify new massive stars. So based on that, we intend to observe the outer disk towards the anti-center direction. First, because this region has a low extinction, and because the massive stars can trace the outer disk better than the low mass stars. So there are just few papers in the literature about this study. So for example, we have the paper from Drew et al. 2026, a very recent paper, where they could identify, using the VFAS Plus survey, they could identify more than 1,600 OB stars and candidates in the third galactic quadrant. Okay, so here we have a figure. I don't know if you can see my mouse, but here you can see the distribution of these 1,600 objects. And here we have these dashed lines that represent the constant galactocentric distance. So 10 kiloparsecs, 12, 14, and 16 kiloparsecs. And these stars are distributed in the third galactic quadrant. And there is also another work, another paper from Bragança et al. In 2019, where they could study in detail 28 B stars in the outer disk, okay? 28 stars from an original sample of 136 B stars identified by Garmany et al. In 2015. And from this analysis, they could derive the stellar parameters of these 28 objects. And some of these objects are in the direction of the anticenter. So even considering these works and also the recent discovery of new open clusters, the stellar distribution in the edges of the galaxies is still incomplete. So based on that, we decided to use the capabilities of T250 to reach the fainter part of the color magnitude diagram compared to Gaia. Because as you know, the limiting magnitude of the JPS filters can reach magnitudes around 22 or 22.5. So we can observe even fainter stars in that direction. So based on that, we propose to observe the outer disk towards the anticenter in a region around -5 degrees and 5 degrees in terms of galactic latitude, and also 170 degrees and 190 degrees in galactic longitude, using the T250 and also TRIPCAN. So it's important to see that this region is not covered by the JPass survey, so we are not in competition with the JPass survey, okay? And concerning the filter trace, we choose to use the T2 filter tray, okay? Because the T2, it has 4 filters in the blue part and also 10 filters in the red part, but covering the age alpha region. So based on that, we think that the T2 is ideal for the identification of hot blue massive stars and also age alpha emitters, okay? So based on that, we decide to check how hot and also cold star can be seen by T2. So Alessandro did this exercise, and here I would like to show some plots. Here we have a hot star already observed by the JPass, and we can see here the different magnitudes in each one of the 4 trays. And in the tray 2, we can clearly see this behavior, of course, unexpected behavior, because the star is bright in the blue filters compared to the red filters. And we see this, of course, the same behavior when you check other hot stars. So we have here another hot star, and we have the same behavior in the tray 2, and you have also the same behavior for this hot star, and also even considering a white dwarf. And you have also the same behavior in the other trays, but we decided to choose the T2 because it covers the age alpha region. And the age alpha is very important for the identification of BE stars, for example, and also some B supergiants. So that's why you want to observing this specific region and also the blue filters. So here we have also the example of 2 cool stars, and we can see that the behavior is the opposite. So the star is bright in the red filters compared to the blue filters. And here also a solar type star. So we can see that using the T2, we can distinguish hot stars from cold stars. So based on that, we check and we saw that the region that we want to observe can be seen at the OAJ from August to December. And this region corresponds to 840 points. And considering that each pointing has 4 exposures of 60 seconds, the total request exposure time is around 80 hours over a 5-year period. And this includes the overhead, okay? So we believe that is a proposal that's not so expensive in terms of time. So concerning what to be done, I think the main task now is to define training samples of different no blue stars, okay, that were already observed by the JPass and that are located in the outer disk toward the anticenter, and that can be observed by us by the T2, okay? And this also includes information from different surveys to get a very good training samples, okay? So to finish the expected legacy results from this proposal, we believe that the large amount of observed data will be analyzed using the different machine learning techniques. So based on our previous experience analyzing J+ and also SC+ data, we believe that the identification of massive stars like OB, BEs, and also hot supergiant will allow us to map and characterize the outer disk in the direction of the outer center. And I think the most important part, our methodology will allow us not only to identify and derive the stellar parameters of massive stars and candidates, but also other classes of blue stars like white dwarfs, blue horizontal branch stars, hot subdwarfs, hot POISE-GB, and central stars of planetary nebula. So we believe that this proposal can feed also other stellar groups, okay, with the data that can be obtained. And the last but not the least, as Alessandro and also Jairo said, I think it's a good opportunity to observe the galactic disk using the T250 and also the JPCAN. So that's it. Thank you very much for your attention.
Well, thank you. Questions for Marcelo?
Marcelo, Alessandro here. I should know the answer, but I just realized that we never spoke about this. What are you thinking of using as detection then? It's literally the same question that I asked to Jairo.
To use what, Alessandro? Sorry, I could not hear you.
So, where does the sound come from? I'm speaking to. Right. Yes. Marcelo, what filter are you considering to use as a detection band?
As a detection, what, Alessandro? Sorry?
Detection band. So
Okay.
you need one filter to detect, and then you extract the objects, right? If you're doing a la JPass.
Okay. So you mean the wide filters or the narrow band filters?
If you are considering, like in JPass, we are using high band, so we detect in high band, and then we extract the magnitudes from the narrow bands.
Okay.
But are you considering also observing in high band, therefore, or are you considering only using one of the narrow bands which are already in T2? You know, this is the question.
Oh, okay. Thank you. Now I could understand. So I believe that in principle, I think we can just use the T2, but we should discuss this better. Maybe you can also use the I filter. I don't know, because the I filter can also be used for the identification of the age alpha emitters. So, but in principle, we can only use the T2 filters.
Okay. Any more questions? Okay, if not, we resume in half an hour, so at 5 o'clock, we start the session about planning your observations with JPCAM for your project.
Okay, bye-bye. Thank you.
Yes? Question, please ask. I don't know. Somebody? No?
Nobody raised the hand.
So see you in half an hour for those online. Yeah? Okay, so let's start the final practical session to plan your pointings for your project. So what I would like for you to do is, for those of you that have a computer and have you have decided your field, whether it is Andromeda or the Galactic Anticenter or Virgo cluster, maybe for those of you that are online, whatever you have, I would like for you to put your coordinates. So I'm going to do an example, but you don't need to do my example. In fact, you should do your scientific case. Whatever coordinates you want to observe, whatever field. So here, my example, I yesterday just looked for, well, one interesting case could be this musket ball cluster. This cluster is in JPass, so It's not observed, and in fact, it's in the tier 2, so maybe it's a good case. But anyways, in JPass, so don't. If you wait, at some point we will have it observed with JPass. But it's just an exercise. So let's know. So what I would do is to start with the pointing planner, and I would put the center. No, well, also Aladdin is also useful. So one of the things I did is to look the cluster in the name in Aladdin. It was already there, no? But just to put the and then I just download the now I don't remember the format, HIPS. I don't. Well, it's a kind of a fix. You can download this. Yes. HIPS250 cutout. So to have a mosaic of this field, it will be useful later on. Of course, what I mean is that you should have some mosaic of your field. It's useful because then you will, at some point, you will be able to point the region we will observe with you are going to propose with JPCam, overplot this mosaic. So what I did is just to download this cutout, and let's see later on. Okay, but also one useful thing when I do the cutout is here I have the coordinates of the object, is the basketball cluster, and then I just put here the coordinates, but put yours, please. The right ascension and the declination. Here you put a name is an arbitrary name. You can put whatever you want. I prefer not put this. So it's arbitrary. It's just a label for the pointing. Then here is the funny thing. So let's start with the corners. The corners are defined in the following way. If you choose the area definition mode, if you choose corners, then these coordinates here are the lower corner. If I'm not wrong, let's see the help, because now I don't. It was open. Okay. It is in the corner area mode. The corner. This is the lower corner. So right ascension is larger than the upper corner, which is A2. So, in the corner area mode, if this lower corner is larger than the upper corner, the pointings will pass around 0 degrees right ascension. So what if the declination should be lower? This declination here, defined here, should be lower, but the right ascension can be lower, the lower corner, but then it will pass around 0. We will see examples. But so let's start with. So I have put here this. So the first corner doesn't make sense to put this because this is the center of the cluster. So let's say we want to observe that if I put a corner, I will put this, for example, and then let's do then, for example, 44. Okay, and in this way, the is a box of 10 degrees in right-hand section, and then in declination, let's also do the same, which will be 24 and 34. Okay. So then, no, I don't know what I've done. Yes, so okay. Then here I have a corner rectangle. We will see what happens. We can choose tray 1, tray 2, tray 3, tray 4. Let's start with the narrow band strategy. This is just the official colors are just is for plotting purposes. it does not affect the pointing definition. And this is if you want to center at some specific filter. This is because maybe you are interested just in observing with, I don't know, with the UHABA filter, no? And then you want to center around that filter your rectangle. The difference with always is put yes always, or you will have problems. And also the differ shift is this one, which is the one recommended. Okay, so you just put compute. So I have put a number. What I have done here? So maybe it doesn't like there was a space. So it's not the symbol is it was a space. Okay. Let's wait. It's a lot of pointings. It's at 10 by 10 degrees by 10 degrees. Okay, probably also the problem is that if all of us are computing things, maybe the computer is not okay. I didn't think about that. Maybe.
What was the problem there? Because I also had the problem that please enter a number.
Okay, it was, I had a space here, so it was this space. But the problem now, and this happened last time, I think, that we are doing, all of us, we are doing the same on a machine that, so now the problem is that.
I'm going to stop mine.
Okay. Yeah, we have frozen the machine.
Also, I think the network is also suffering a bit.
Okay, so please no. So then don't do the exercise at the same time as me. I didn't think about that. The computer is
Do the exercise, but with a little bit of delay.
exactly, and please. So okay, don't do that. Please let me. And maybe we have broken the computer. Let's.
Can you please give the link? Yeah, I was away when you.
He was at the toilet.
Yeah, I didn't say the link. Sorry. So it's there.
If you go to the page of the observatory, then you go to observing time and observing tools, and then there is the that you can select.
If you look in Google, become panel.
No, really? But that good.
But the problem is now it's not working. It should. I don't know. Probably it's because all of us are using the tool, and I hope it's that. So, it is okay. So normally it's faster, but because we are using the tool, okay. So here we have it, no? So then this definition is to have these corners that I said, which is between 30. So in right hand section is between 134 and 144. So this one is 134 and 144, no? And then in the combination, so similar, no? Between 25 and 35 is more or less. So okay, so here you have the pointings to observe that rectangle and to observe this area, which gives you 92 square degrees. You have to observe almost 600 pointings. So things that are useful is to download this. Okay, so yes, download it where you want. And then, because things that are useful, I have it here. Okay, so I open the mosaic that I downloaded in Aladdin. You can open your mosaic. All of us are astronomers. You can find a mosaic you like along your field. using Aladdin or the or a specific survey you like, and you know that covers your specific region. So I'm going to open this mosaic I downloaded yesterday, and then this one, okay, and then I will load the region I just downloaded, which is this master folder. Okay, and you can see the mosaic. You can see what area in common for all the filters we are going to cover with these pointings. Okay, so important thing you should notice is that probably this limit here, well, it has an error. So please use this if you want to be sure of the borders, like you need a very specific or some specific objects to be inside. Please take care of the border, no, because it's not exact the solution. So in fact, I said no, the corner was in the lower corner was 134, let's say. So let's see, which is 134. So here we are at 100. Well, it is inside, but maybe not always, no, because in fact it's not. Probably it's not a straight line, or it can. I have done this tool and I hope it should work, but well, sometimes there is maybe a 1% error on the borders. So please, if you worry about the borders, be careful. And this is the only thing you have to do is to plot it on your region and check it.
It would be fun to have 100 square degrees observed, and then you have a problem with 5 arc minutes because of pointing, right?
Exactly. Okay, but it's 1% of the, I would say, or even less, the error on the borders. Some more things you can do. Okay, is, for example, I want to do one thing. What to do? Okay. Well, we have done the corners definition. Remember that if you, so I have introduced a lower. So in this box, the right ascension is lower than this right ascension, no, the one the name 2. If this is if I put here, for example, 124. It's not going to work. In fact, it's going to freeze the tool, because then it's going to start. It's going to try to go through 0 right ascension. This is in case you want to observe around 0. You need to 0 right ascension. You need to put then you need to change or to inverse this right ascension declination. If you put, for example, here, this is going to fail. So this is going to tell you deck 2, the second declination must be larger than deck in data. Well, this is the corners. Let's say maybe it's kind of simple to think about this also using a center and then defining a box for your survey. So here, well, I will put this 20, no, which is the original one, and then 39, and then let's say, well, here it put, for example, if I want now a smaller box. Before was a 10 by 10, so almost 100 square degrees. But then let's see if I put a smaller box also, in order also to be quicker in the computing time. So if I put 8 by 5. Okay, so now it's a smaller box. It's a 35 square degrees box, and you need almost 300 points to cover that. And then I can also download. Let's name it like that, and I also can open here the regions just to compare. Why is not? Well, okay. Oh, no, something very, I did something very wrong, but this is why you need to check. So yes, it was 29. So my mistake. You can do these mistakes also. So please plot your region, the region you are asking, plot it in DS9, just to be sure that the pointings are what you want to observe. Let's see. You have it. The differences depending on the declination is because of projections between CCDs. Well, I'm not going to go into details. Yeah.
Javi,
Yes.
just one question.
Yes.
So this works in right ascension and declination.
Yes.
But for example, if you were to observe the galactic anticenter,
Yeah.
and you can only define, I see the top left corner and then the right bottom corner. Is there a way to, like, because this field is not going to be a square, it's going to be like this.
Yeah.
So is there any way to do that?
If there is a way for you to do that, Alessandro has done it. I haven't done it, but there is a way to do that. Alessandro has done it. Yeah. I don't make cloud, but cloud. I don't know.
So what I did was I generated a list of pointings between some galactic coordinate limits, but I generated that list of pointings in red ascension declination, and then I generated those pointings, and then there is if you go up,
yeah,
you go to that arrow there. And then that is where you can upload your own list of pointings. What I can do is I can pass you the script I did, the pointings I made. Huh?
You use small pieces of the sky
Yeah.
to build the whole.
Yeah, basically. Yeah, I made a grid of pointings.
Oh.
It's literally, I basically did the same list of pointings that is from JPass, but instead of doing the whole JPass, I only did the galactic.
So yeah, one important thing about it, you can define your pointings in the coordinates you want, and then what the observatory wants at this stage is the equatorial coordinates. We just accept at this moment we just accept the equatorial coordinates. But you can use this to find your pointings, and then you can upload the file and check what is the area. In common, so the output is the same, but it's important. Well, maybe this option is important. So always the problem is here. So if you want to observe because of something, whatever reason, at the end your pointings are around 0, it doesn't accept the negative values of rate of transition. So this option is just to shift the ones. The ones between 0 and 180 degrees in rate transition, it will add 360 degrees, and then it will be continuous. So, if you have problems using this and you are observing around 0, you can ask me, but this option is needed to be continuous. But just ask me also if you have problems with this. I'm not going to explain this advanced tool. If you want to use it, define your pointings and use it. You can always contact me because it's not straightforward. And I will focus on the others, on these default pointings. Okay, so now I just
I saw parameter called radius in the adaptive tool.
Okay.
That means that we can select our pointings around 30 distance.
No, this is if I'm not wrong, is for plotting. It's just for, okay, now I remember. It's because this tool doesn't know so you put your pointings, but this is just to put the centering. At the end, this is matplotlib, so it's to do a zoom on around this. So this, you have to, sorry, this is also important. Thank you, Luis. This is just for plotting purposes. You put the center of your pointing, of your field, and this is just for plotting purposes. The center and the radius is plotting. It's saying matplotlib, which is the center of the figure, and which is the radius of the plot. So it's like this. Right? Zoom in this and this center and this radius. So it's not important for the definition of the pointing, but it's just a view thing for the viewer. Okay. So we download the regions in DS9 to check. Now I have made a mistake before. I hope now not anymore. Okay. Again, this is why you should check your pointings and before submitting and doing your calculation. So now they should be fine. Okay, now they are in the center. So and you can check. Well, is this galaxy, which is very important for the project? Yeah, okay, it's inside. Okay. Oh no, but this is outside. Okay, so no. And this kind of things. Okay, let's continue with the other options. The MPs option, the MPs is like number of pointings in the right ascension direction and the declination direction. This option was the previous one. I like more the rectangle, the definition with the rectangles. So if someone wants to see what happened with this number of pointing, the MPs option, because if not, I skip it. Now I prefer the corners and the center definition. Okay. Someone online. If not, you can ask for it when you want. In my case, what I think is easier to understand the center. The corners may be more complex to understand. Well, no, not very complex, but okay. But the center and size of the box is very, very simple. Okay, so now also important, maybe you are interested in the blue filters, for example, in JARRAS, in JARRAS. You are interested just in blue filters, so you can do, for example, well, what happens if I just take into account the blue filter, which are on the center, because of reflections and goals. So what happens then if you can just select some specific filters, which are now, for example, the blue ones, and then see what happens. And define. Okay, now you need. Well, in this case, okay, yeah. In this case, the area is defined for all of the filters in common, but what you have is in common, you have more area than before. So your rectangle here is not defined, is larger than what you need. So maybe you could play with this, like put a smaller value. So the calculation, it doesn't change. It's the same number of pointings, and the rectangle is larger at the end. Your rectangle is larger than what you need, but then you can play here, for example, less numbers. This is because the estimation of the rectangle is made considering all the filters. So this is just for plotting purposes. What happened with just some specific filters? So you will have you have more area observed than what you need. So you go much more. So your box is larger than what you have input. But you can play, and here, different numbers, and then make a smaller your rectangle, and at the end have the area. You always can download the pointings, the region in common with all the filters, or the filters that you have selected here, and you can download the regions for each filter.
If you download here, you download that zip file. And then, yes?
Can I say something about this filter selection?
Yes.
Would it be possible to rearrange the filters in order for them to appear the same as in the CC? You know what I mean? For example, the
Yeah.
4 central ones
Yeah.
in the middle, three on one side, 3 on the other side.
Yeah, you mean, yes, maybe.
I mean, if it's not very difficult,
Yeah, well.
because it would be. Well, I
Yeah.
know how it works. I mean, for me, it's not a problem anymore.
Yeah.
In the beginning, it would have been nice to just see.
Yes, it could be, yeah. Send your desired list. You can always send it to the email, and it would be, it will be taken into account at some moment.
Will be taken into account into dev null.
Okay. But no, thank you. Thank you for all the comments. I mean, this tool it has improved also due to your feedbacks, all of you. So please, I always I have done changes since the beginning, I think. Okay. So let's for example make an example. Then I prefer to select all the filters. So let's go here. Compute it. And now what I'm going to do is to try to find this what pointing need to be done to do the same or to cover the same area, but with the broadband strategy. So now what I choose is the broadband strategy. I don't select this, the no cover gaps option, we will see it later, but now let's say, okay, the same box, no, the 8x5 box, and then I compute what are the pointings in broadband to cover the same region. This should be quicker, in principle, because it's far less pointings, in fact it's 48, and then, then is this area, which is a lot, then we download the region. So it's 48 pointings in total. Here. Road, and we open it here, and I will put other color. Which color? Okay, no, I can. Well, in green. Okay, so I will just do. So remember, this is the one inside is the narrow. I will change the color. Okay. The green one is the narrow band, and the blue one is the broadband region. So here, for example, you can already check a problem. So in fact, here maybe you are not covering the same area with the broadband than comparing with the narrow band. So maybe you should make a correction. Like for example, then here what I have. I have seen that I need maybe a little less declination. In fact, we can measure it. What it is between the declination 27.4, so it's like 0.2, 0.3 if we want to be sure. So let's put here. I have reduced the declination by a factor or by 0.3 degrees, yes, just to shift the broadband to cover the same area, because I have realized that there was some area which was not in common. So now I download the user interface. I'm going to replace the okay, and I open the region. So it's important for you to plot your regions. It's important. So it's blue. Okay. Okay, now it's much better. well, still maybe I should put, oh, sorry, I need to change the color. In fact, I should put a little bit more because then if you are, if you are, if you are very detailed, no, then there is some area, but well, as an exercise, it doesn't matter. But for your project, I will be, no, this area is not, no. I mean, and the thing is, it doesn't, then you have this area is going to be wasted. So it makes sense to just download a little bit the declination, no? I guess you understand what I'm saying. Sorry if I'm going very quick. I want to say a lot of things in this time that I have. Okay, so I guess this is clear. Once you have defined your pointings, always if you have problems, doubts, ask me now or tomorrow or by email. I will be very happy to help you to define your pointings if you need it. But once you have defined your area for your field, and the number of pointings, so remember, because maybe I forgot, we have 48 in broadband. Now I don't remember the number we have. It's 300 and something. Okay. Because it's important to have this number. Well, 48 and 350. Okay, don't forget, Jairo, please. Well, now what we need is to use the specific calculator to know how much time we need to reach our desired there. Okay, now well, we have, for example, here 22 magnitudes. Let's go, for example, for the filter, because it's a round number, is the 500 filter. We will put all the trays in the narrowband trays. So I like more, for example, let's not put the time, but just what you want. For example, 5 sigma, 5 signal to noise ratio on 22 input magnitude in this input band. And okay, and for example, that time, and I could press calculate, but then something is missing here. Do you know what?
I mean, this point is regarding the earlier question. At this point, you are establishing that input band as the detection band, or this is not related.
You can define the detection band afterwards. This is just to decide what is the depth of your observations. You have to define the depth of your observation in all of the filters, but at least to start, you need to choose one filter.
Yeah.
To start. So what now I'm doing, but you can do whatever you want, is because it was there, is, well, let's start with, I want a 22 magnitudes in this filter, in the 500 filter. But but you can go to H alpha or the depth you want. I mean, the depth is the magnitude, but then, well, the depth, but in which filter? Yes.
So you write there to
For the
you select all the traits.
yes,
You will get all this.
yes, yeah. We will see the result. Yeah.
My question is, the magnitude that you put up there will relate only to the 500 feet?
Yes.
Or will it be, for example, in U, 22U?
We are going to see the output now, but this is to do the estimation of the. So this gives you this input here gives you what the exposure time needed in 4 exposures to reach 5 a signal to noise ratio of 5 in this filter, in 500 filter. So we will see the output, maybe when we see the output, it's clearer. But before that, here is something is wrong. Do you know what? I mean, I've done this a lot of times. And
There is a different thing if it's a hot star or
no. Well, no. There is something which is very wrong, and I would like someone to point. But yes, David, yes, it's the meaning. So I said before, so and please, so if you do this calculation for narrowband trace, if you want the output for narrowband trace, put the binning 2. Okay, the gain is here. The gain, for example, it doesn't change. You can put here 1 million, but it's there. I don't know why, it's my fault, but the gain, it doesn't change. This tool doesn't use this value for the calculation. But yes, the binning is 2. If you are going to do this calculation for narrowband filters and trace, please put binning 2. And for broadband, use 1. So congratulations, David. I'm very proud of you. Okay. So now the output. What does it mean? This? So what? Then the calculation is done. If it's not wrong, is in this filter in 500. The output is okay. Is 5. So you have 5. The signal to noise ratio of 5 in this filter, observing. Because it's what we asked for. So we asked, please give me the exposure time you need to reach a signal to noise ratio of 5 in this filter. And the result is 36 seconds. But then in 36 seconds, you have different signal to noise ratio in all the other bands. So in UJava, you have a signal to noise ratio of 3, and and it's plotted here. Sorry, here, the signal to noise ratio. So you have signal to noise ratio between 2 and 10. But the calculation is done for this input band. Okay, let's go. If you use other filter and you do the calculation, okay, but for this filter is 550, you need 46 seconds. This means that in the calculation has been done in this filter, and then you have 5, but then for the filter that we did before, we have a signal to noise ratio of 6.1. Okay, but then things that you can, this means for exposure time of 4. Sorry, the number of exposure is 4, which is, you always need to put 4 or multiples of 4 to do different. If you don't care about the background subtraction or the flux calibration, you can maybe not use the different pattern, but it's much better to use it. Okay, so I guess this is clear. You can input your here we have some templates for the stars, AGNs, galaxies. Let's use a galaxy, for example, a galaxy, a spiral one. You can also upload your specific spectrum, but then also the spectrum is going to be normalized in the input band or the reference you choose. Let's use for the input band because now I don't mind, and then for example it's a galaxy at 0.2 resistance. So then you are going to plot the signal to noise ratio is going to take into account the different magnitudes depending on the wavelength. So this is also very useful if you know what kind of objects you want to base your depth estimation. And you can change here the input band and the reference. So you maybe want to normalize the normalization band to other band. Okay. This is, for me, this is a very common exposure time calculator before before was more complex, but now is like more standard, I guess. It's similar to other exposure time calculators. This doesn't take into account the number of pointings. So this is just to know how much time you need to expose they become and the number of exposures. So, for example, you may are crazy and you think, well, I want 24 magnitudes because you think you can, but and then okay, so you can do the calculation and then of course you need a exposure time of 1,700 or 1,800 seconds. Yes.
Would be the single exposure time.
Well, this is the time for a single exposure time, but considering that you made 4, so at the end you have 4 exposure times.
Of one.
No, sorry, it's four exposures of 1,800 each.
So total in this case, we have 12. No, yeah, 12.
Yes, 2 hours, yes. Well, 2 hours on source, then plus overheads, but then we will talk at the end. Okay, but then this is impossible. You shouldn't ask this. If you do, I guess the thing is even not going to go through the scientific panel. So what you need to do if you want to do this, then you need to increase your number of exposures. So it's not 4, but I guess a multiple of, let's start with 24, and then do the estimation. I guess it's going to be a lot more. But well, it has increased a lot. So maybe 24. So now the exposure time you need. This means that you need 24 exposures of 300 seconds each. Still, it's not valid, but we are close because the maximum is 100 seconds. So now 170 almost each exposure time. So maybe let's go. I'm multiplying by 2 all the time. Okay, Okay, now we are maybe even less. Let's. At least at the beginning, this is what we need. Even here. So yes, now this is the exact number. So you need 88 exposures of 100 seconds each to reach 24 magnitudes at a 5 with a signal to noise ratio of 5. So well, and in this band in 550 this filter. And then what you would observe of a galaxy, a Resi 0 galaxy with a Resi 0.1, it should know you will have this signal to noise ratio in each of these bands. So if you are interested on the red, so it's probably is better. The signal to noise ratio is much better. So well, this may be a crazy. Well, this is too much time, you may think. Well, I don't know. You have to do the experiment. So, but let's also think in the other way. So, if you delete this number, then you can put here the exposure time, which is 100 seconds the maximum. Then you cannot write here in the signal to noise ratio. Then you have to delete this number to allow this one, to allow the number. But let's be more like less ambitious. 23, and then well, even 22.5. Let's go to a red filter. Let's, for example, the 600. Yeah, get it. Okay. And then, for example, here for exposure, let's check what is the signal to noise ratio. It's not very good. Okay. Let's make 8, for example. Check. Okay, now it's a signal to noise ratio of 3. For in fact is 5 in the red part. No, so it's not that bad. No, in the red part is very. The signal to noise ratio is between 3 and 6, but it's not that bad. So for example, then let me. So if you are already happy with this, with the decision of having 8 exposures of 100 seconds each for the narrow band trace. So remember that we have the number of pointing was was the number here, 315. So let's put here, and then is 1 second, and thanks. So let's check the total time of this project for one train. So you put that. And then is 19 or 19 hours, almost 19 hours. So if you want to do on the trace, okay.
Signal to noise 5.
Well, now this is signal to noise 5. I didn't define with signal to noise ratio, just I put 100 seconds.
Okay.
But you have signal to noise ratio of 5 in this, for example, in this one. For a galaxy, a spiral galaxy. Okay. So now.
Javier?
Yes? Yes?
I had a question. What is the nominal seeing at Javalambre?
Well, I would say one a second, but the reactor.
Obviously.
That's a reactor. You are the expert also.
No. I'm getting closer because otherwise.
There is the hello.
So, hi. So it depends, as you know, as you all know, depends on the wavelength. On the reddest wavelengths, you have lower PSFs, but the median is about 1 second. We can reach in the best cases we have reached even full width maximum below 0.4. We can have this kind of full width maximum, but the median is around 1.
Okay. Thanks.
Amin also has the hand raised.
Yes, please.
Yeah, thank you. So yeah, I have a question. So in the exposure time calculator, you have an option to select like extended object. When you should use this one? Because I see that there is a galaxy tick that you can select if you want for galaxies. So how that works? So for example, in our case, in the proposal that on the letter that we sent, we aim to observe galaxy outskirts mostly. So in this case, to do the estimation for signal to noise ratio, should we use this extended object option or using just galaxies is fine?
Yes, yes, very good question. There are a lot of possibilities, and so thank you for asking. Don't be shy, please. So yes, if you want if your science or your project definition needs to be defined for an extended object, you need to use this option. You need to check the extended object, and this means that the estimations are going to be estimated. So if I press here calculate, the units they are going to change. Now is the signal to noise ratio is defined. This is defined within a pixel, and this and this is the signal to noise ratio is going to be or the magnitude is going to be defined per second square. So at the end, what is important is that in fact yes, this is the signal to noise ratio within a pixel. Probably yes. Let me check. I mean, I did this few years, 2 years ago. Now I don't remember. So what is in the okay? The object is extended. Check this box. If selected, the aperture diameter will be disabled, and the output information counts and signal to noise ratio are defined within a pixel, while the input magnitudes are defined in magnitude per second squared. So if you are interested on the outskirts of galaxies or in whatever region in the galaxy, you define your depth in magnitudes per second squared in some specific band or filter, and then you estimate the signal to noise ratio within a pixel. I don't know if this answers your question, but Mari Carmen?
Yeah, that's fine.
Okay. So
yeah,
yes.
that's exactly the question. Yeah, so we did okay in this case. We just now had to change the exposure times to be within the limit.
Yeah. And always, if you have doubts, ask me, and I will help you. But using these galaxies or stars, this doesn't change the definition of the extended or not, because galaxies can be also unresolved. So this is just going to change the dependence of the magnitude with the wavelength. No, not any. So this is just going to change the input spectrum if you use it. Maybe you can just use a constant one. Okay, so then what I was also trying to tell is, well, how much time I need to reach this signal to noise ratio of, well, or how much time I need to do 8 exposures of 100 seconds each to cover the area we defined before, which was using 315 pointings. So then I put this number, the number of pointings, the exposure time, the number of exposures for each of the trays, and then I calculate the total time, and it's 350 hours, 54 hours. So for 5 years, this is not crazy, I think. It could be done. Of course, it's hard, I mean, because it's that time, and also depends on the observability of if your object is just observable during 1 month, for example, because it's very low, or so it's going to be very hard to.
How much time per year was
It's 240 hours per year, but for all of the conditions. And at the end is on average, because also this depends on the weather, but on average is 20 hours per month, so it's not that much. 20 hours for all of the conditions. So think about the time. Also, you can ask me how much time I think, because the problem is that we don't have a number. For the gray time, gray, dark, and bright, we have a number. And well, just for you to know, we are using the dark, gray, and bright time here is realistic. Even the gray time is even better than the one we are using here, but okay, I prefer to be conservative, and but so is dark 50%, gray 25? Yes, dark is 50. Yeah, but this is also in the GTC, for example. So but the problem here is also that it's photometric and non-photometric is also variable, and it's not as easy to quantify as the moons. And so there are also, if you want dark and photometric, is 50% plus some percentage that I can give you privately, if you are interested, or maybe we publish this number in the release call for proposal release. Okay.
Yes. Would it make sense for someone to propose to us in the proposal to say, I'm asking for blah number of hours in dark time and blah hours in gray time?
Yes.
So
yes.
splitting your project between dark and gray.
Yes, of course. Yes, and bright time also. Okay. Yes, like JPass, for example. But also one of the recommendations I gave in the talk is that also you can say, okay, I'm asking for 500 pointings, but I can do science with 200. This will be very helpful for the evaluation because in case, for example, your proposal is maybe the third one, no? The third is rank you are the third in order in scientific ranking. You are the third, and maybe there is no time to observe all of your project. And then the cat says, okay, so your project is not approved. But then you say, well, but with less pointing, then it can be done. Then maybe your project is approved. So you can also make not several proposals, but make this area is what they want, but some of the scientific goals can be performed with less area or less deep, for example. So, well, yeah, this is a very good recommendation. It will be very helpful for you and also the CAT and the observatory. But because if not, maybe your project is not going to be approved because other projects are higher in rank and there is not enough time. There is not enough time for your project. Okay, more things that I wanted to say about this thing. It's important for you to use this project total time. There are, for example, one project that said, well, I want to observe, I don't remember now, like 50 pointings, for example, then is that time. And they did the estimation by themselves. No, use the project total time because we have overheads and we have to take into account the overheads. So don't consider and are more than the readout, the download, the moving of the telescope, but also the optical alignment and the actuator's movement. This can change with time, but and this change with time because we are maximizing we are parallelizing this movement and the overheads, but still you need to use the project total time for that estimation. I think the exposure time calculator for me is clear. I have done, of course, I have done myself. But I would come back to the pointing planner to say one last thing. But there are questions about the ETC.
Not apparently. In any case, my connection is very unstable. So if you have a question, just unmute yourself and ask.
Okay. So one last thing, because maybe there is interest. So is when defining your the broadband. So the broadband, the people looking for asteroids or other things in on the sky, they may prefer to maximize the area, although having gaps. And then so just for you to understand what this no cover gaps option makes. So if you check this option, and I prefer to put a small box. I prefer a small box just for the beginning. Okay. It's not well seen. Okay. Let me put, I don't know. Now I don't know. Let me remove the littering. Don't see what don't see what I'm doing. Okay. I'm removing the littering just to also for you to understand this what is doing this. Okay. Let me put the now. So let's make a one pointing. Just to understand what is JPCAM with no gaps. Okay. Here we go. So this is the area you have if you just observe with JPCAM pointing to these coordinates, one pointing. Number of pointing is 1 by 1, but then no covering gaps. So you have this. What happens if you say, okay, give me in the declination dimension, make me 2 pointings. So you have this. You maximize the area, but you have gaps. Then, okay, you say, okay, give me a 2 by 2. Maybe it's going to fail, sorry. To fail the plotting, or not the, no, it's okay. So this is a 2 by 2. But then the problem with this strategy is that you have gaps, but then you have more but you have more area, a lot of area. With just for pointing, you have a lot of area, but it's not contiguous. But for people looking for things, I mean, if you don't need a contiguous area, this is the way to have the maximum area. But please, this is the use dithering. I just didn't put dithering in order to see the okay, right, the dithering makes this, so this is the area you will have with the different the area you will have inside these boxes, the red boxes is the one that have been observed 4 times with the dithering. Okay, this is also, I mean, this is very useful for some of the projects. In fact, this is here because there are people that has asked for observation without covering the gaps. So this is here. Then this in principle it also works. Here this, like the boxes, it should work. And then it gets more complex to understand, no? But well, maybe it isn't. Okay, so this is all I wanted to say. This is all I wanted to say. I don't know if you have questions. At the end, when we release the call for proposal, what we will need is this output, the project total time. Which is this, of course, give us these numbers also. I mean, these numbers, the depth, the depth you are. I mean, yes, describe all the call for proposals in the proposal. Describe all of the input you have. You have put here in the tools, and also it is mandatory to share with in the proposal the figures that appear here. If it's strange, because sometimes the Zoom can fail, please let me know, and we can manage to help you. The CSV, so this CSV is not we don't require this in the code. We will not require this file. This will be required to use it in the phase 2. They become phase 2. But well, the number of pointings is important. Also, if you plot the DS9 region overplotted in over your field, this also would be nice in the proposals to have. And I guess that's all I wanted to say. So thank you. 6 o'clock is late for all of us, but I'm always happy to help you. So please contact me if you need. And see you tomorrow at 9 o'clock to start with continue the scientific discussion about of the projects.
Okay, thanks, Javier, everybody. See you tomorrow.
See you tomorrow.
Yeah.
¿Qué pasa?